Yeah, good morning, everyone. Welcome to Houston Oasis. My name is Ted Andrews, and I'm the MC for today. We traditionally open the meeting by highlighting one of our 5 core values. And today, I'd like to consider be accepting and be accepted. This one is basically true by definition, because if you're a member of an accepting group, then you will be accepted. And Houston Oasis, as a secular community, it's fairly natural for them to be accepting of others. We don't worry about a person's sexual orientation, their belief system, their cultures. And that's one of the reasons that I really love being at Houston Oasis, is because of this core value. We've got a good lineup for you. Yeah, enough preaching there. We've got a good lineup for you. Today, our musician is Ryan Biter. And you may have seen his bright red convertible in the parking lot. It's a beautiful little car, but he confided to me that it's not really his car. But anyway, it's a beautiful little car. And he's coming in from Arizona. He's a master guitarist, as you heard here, and singer-songwriter, and obviously a nationally touring artist. So we're looking forward to hearing from him. And our main talk is a continuation of last week's talk on the theory of everything by Dr. Eric Schmitt. This, I'll confess that if I said I understood half of that theory, then it'd be untrue, but I understood a little bit of it. And I did see the video, the YouTube video, which I'd strongly recommend. It was amazing how well done the video was. It was easier to understand the video and see the screen on the video than it was in real life, which was quite a surprise to me. But even though I didn't understand everything about the talk, I thought about the talk for the entire week. And it seemed like I was seeing elementary particles everywhere I looked. And I don't know if that's just my imagination. Maybe Eric can tell us if we really can't see them, but so I guess, Eric, we are ready.
Okay. So do a little recap from last week just to get you refreshed, and or for those who weren't here up to date. So first of all, I'm not a physicist. Okay, none of my degrees are in physics. So this is just thoughts that I've had after having an idea several years ago to see where it would go to. Basically, what we did last week was produce a bunch of strings through a phase state from points. And then and if strings sound weird to you, they're dimensional strings. This is a string theory. So that notion is already out there and well accepted in parts of the physics community, that there could be these dimensional strings. We used those to do 2 things: to build space and to build the contents of space. So we took a closed loop string and turned it into a preon. So you just fold it up into 3, and we're going to use that to build particles. The first particle that we built by sticking 2 of them together was the photon, and frequency is explained by rotating one end relative to the other. And we've got an electric field and a magnetic field. So these are monocharges on the ends. Rotate, if you move charge, you generate an electromagnetic field. If you put 3 of them together, you get these things that correspond to the gluon color charges. In the standard model, that's what holds the quarks together. I use them differently. They go at the ends of the structures. The quarks in my model bind directly to one another. So these will actually allow you to join, to allow protons to approach each other, because in a nucleus, to positively charged proteins should want to fly away from each other. You need a way of gluing it all together. And that's what these do. So that's when you have 3. And where we left off last time was what happens when you get 4, when you stick 4 of these prions together, and you get exactly 4 structures. And it turns out that if you look at your standard model, the columns are exactly 4 items. So almost all of the universe, everything you meet is made of the up quark, the down quark, the electron, and then there are also electron neutrinos, but they don't really interact with matter too well, with the rest of matter too well. So it's the right number to be what are called the generation 1 fermions. And so we're going to take a look at that and see what that gets us. And then if you keep assembling, so that's 4 together. If you put 8 together, you get another set of 4 structures. And we'll talk about those. And I'll show you why I believe those to be the force carriers, the bosons. And then all I do is continue building so that you duplicate the ends. So here's 2 up, 2 down on the ends. Same thing for this. Same thing for that. The generation 1 fermions, generation 2 fermions, and generation 3 fermions. So with that, let's get started on the slides. Okay, so as I say, if you put 4 prions together, you get 4 structures in the left column. And we have to decide, it sounds like one of the, and then we've got 4 if we stick 8 together. So we've got 4 of these fermions to account for. We've also got 4 remaining forces that we have not accounted for. The first one we did, photon carries the electromagnetic force, but there are W plus, W minus, and Z bosons that carry the weak force. And then there's the Higgs boson, which is a manifestation of the Higgs field. So we need to come up with all those. Well, we've got the right numbers of those. So which is which? Well, the structures with 2 or 3 prions are massless. That's the photon and the gluon colors that I showed you. Those have no mass. When we get to 4, all of a sudden we've got a square in the middle. And so that must be associated with the acquisition of mass. And the other thing that we can know is that these structures over here on the left look almost identical, yet their properties are different. They have different charges, they have different masses. And so it's going to depend on what's different about them, and that's these half bond ends. So if you stick 2 half bonds together, you get a full bond. But on the ends of the molecule, you still have on the ends of the structure, you still have a half a bond that you haven't connected to anything else. So the charge is conserved across rows of fermion generations. So if you go across one of these rows up here, you should have the same configuration of ends. They recapitulate. That's what I had just shown you. So that's how we're going to maintain charge across the row. The structures are getting bigger. So that's how we're accounting for increase in mass of the particles as we go from generation 1 to generation 2 to generation 3. So how do we decide which is which? Well, this yellow cube here, that's a dead end. I can't extend that out to recapitulate the ends to get to a generation 2 or generation 3. So that can't be one of the fermions. This has to be a boson. And that means these structures made of 8 prions are the bosons. We've got our Higgs boson, where it's the heaviest of the bosons. So each of these squares is, I will show you in talk 3, and I'll get a little bit of it in today about how these end up producing mass. And so those squares having that many of them means that's the Higgs boson. Everything is balanced on it. So there's no charges, there's no half bonds sticking out. It's going to be charge 0, and the Higgs boson is charge 0. And the next in mass to the Higgs boson is the Z boson. And if you look at these structures, this has 1 open bond, and then this has 2, and this has 2. So W comes in 2 forms. There's a W plus and a W minus. They just differ by charge, but they're the same mass. So the ones that have the 2 open bonds, those should be the W bosons. The one that has only 1 open bond should be pretty close in mass, closer in mass to the Higgs boson. That's the Z boson. So down here we have the Z boson, and then we've got a W plus and a W minus. How do we decide which one's which? Well, one of the fermion structures has to correspond to the electron neutrino, and the electron neutrino has no charge and very low mass as a consequence. So charge actually plays a very big role in producing mass because these structures are nearly identical. So figuring out W minus from W plus, the yellow boson here is the Higgs, as I said. And so the so the orange structures here, because these have 2 bonds, these are going to be the quarks. They bond to the gluons, which also have these 2 bonds on them. That's how they connect down at the base of these. So that's how we know what the quarks are. So we've got the orange is either up or down. And so we have to figure out which is which. Well, up is positively charged, and one of our bosons is positively charged. So that would work for that. Okay. So in figuring these out, these actually have diagonal bonds. And one of these is the electron, one's the electron neutrino. This one's an oddball. It's only got 1/2 bond on an end. So it's behaving differently than the other ones. Looks like it ought to be the Z boson. Makes that the electron. These match. So there's one negatively charged W boson. It's got a -1 charge. The electron's got a -1 charge. Fits to stick these together. And based on similar end configurations here, that would fit with this being up and this being the W boson. By elimination, that's the down boson, and also by process of elimination, since we've got this assigned to W minus, and we had already decided that this was the Z boson based on having a single open bond, that makes this the neutrino, which also has no charge. Complicated argument, I know, but it works out. And I have to say that, and I'll show this another time, you can calculate the appropriate charges and masses for these structures based on those assignments. So here's our 3 generations. We're recapitulating the ends, and that carries charge, the same charge across a row. And we have mass increasing from left to right as the structures get bigger. Now you can build things in between here, but they don't have the same configuration of half bonds, and you get things that are planes that are perpendicular. So here, these top 2 half bonds are in the same plane as the bottom 2 half bonds. But in between are ones where they're set at 90 degrees to each other, and presumably those are unstable structures. Well, For the neutrinos, one thing I wanted to tell you about is they have this weird property that they oscillate. And where you change from, there's 3 generations of neutrinos, the electron neutrino, the muon neutrino, and the tauon neutrino. That's the bottom row of your handout. And they change from one type to another. It's common to call them flavors. Now, how do we know that? Well, there were measurements of neutrinos from multiple sources that didn't show the right number of neutrinos that they were expecting to see. And that included studies of solar production in neutrinos, decay events in the upper atmosphere, nuclear reactor production of neutrinos, and then neutrino beams as well. So there's this big deficit, actually. It's for the solar count, it's a third of the expected number of neutrinos that they're seeing. They had to figure out what was happening to these. Well, the deficits were due to neutrinos, electron neutrinos is what they were looking for, changing to these other forms, the muon neutrino and the tauon neutrino. And the best evidence for that, really, one of the clearest ways to see it is they used accelerators at different locations, separated by big distances, and did that 2 places in the world. And they created a beam of electron neutrinos at the source and shot it towards a target and measured what showed up. And what showed up was fewer of the electron neutrinos than they expected to see. And they did not send muon neutrinos or tauon neutrinos, but at the receiving site, they received those. So these things are changing form. The way the standard model deals with that is they say that the neutrino is a superposition of these 3 things. And they say that even though these have different masses, and these are fairly different masses, this is in electron volts and this is in million electron volts. Personally, I don't like that idea. And, you know, they ignore the mass argument here, but then for electrons, they say that you don't cycle from, say, electron to muon to tauon because they're too massive to permit that. I've got a different idea how that all works. So we've got our Z boson here that we just talked about. And if you take an electron neutrino and you couple it to a Z boson, you get the muon neutrino. So just join those together and you can reverse that process. So you can take a muon neutrino and split it apart into a Z boson and an electron neutrino. You can also take this muon neutrino, add the Z to it and get the tauon neutrino. And that process is reversible as well. So then you'd ask, well, okay, why doesn't that happen for some of the other particles? Why don't positively charged quarks combine with the W boson to cycle like that? Why doesn't the electron combine with the W minus boson to cycle like that? And the reason is there's a charge interference. There's charge repulsion between those. A W plus quark, a positive quark has a positive charge and the W plus boson has a positive charge. You can't bring them together. The reason it works for Z is Z is uncharged and the electron neutrino, the muon neutrino, and the tauon neutrino are all uncharged. You can bring them together. All right, so there are up quarks, down quarks, electrons, and electron neutrinos. Great. That's our first generation fermions. But it turns out that there are 4 of each of these. There are 4 different kinds of up quarks. So one is they differ by whether they are matter or antimatter. So matter has what's known as left helicity. Matter has what's known as left helicity. Antimatter has right helicity. In there, there's also chirality. So there's a left chiral and a right chiral up quark. And same thing for the down quark, a left and a right chiral, same thing for the electron, same thing for the electron neutrino. So you've got them for matter and antimatter. So we've got 1, 2, 3, 4 of these. How to account for that? When I build these structures, I've only got 4 structures. How do I get the helicity and the chirality out of this? And also, when you look down these columns, there's some things we haven't talked about before. This is Q is charge. So up quark has a 2/3 charge. That charge is related mathematically to 2 properties called weak isospin and weak hypercharge. So here's the weak isospin, here's the weak hypercharge. And those values change for the weak isospin and weak hypercharge as you go from left chiral to right chiral. All right. Well, all of these things are related to a spinner. A spinner is this structure we talked about last time. Easiest example of that would be a Mobius strip, where you have to go around twice to get back to where you started. Take 720 degrees. We can get these properties out of a spinner. So let's add a spinner. So my first attempt to do that was to make caps to go over the ends of the fermions. The idea was that the particles carry charge and you want to rotate that charge relative to the spinner. So I was trying to cap the ends, but everything I built was pretty clunky. I could get things that had multiple paths, but it wasn't quite clear why that would take 720 degrees to go around it. And they had lots of prions that went into their structures, so they're hard to make. And we wouldn't expect those to be an abundant product as the universe was born. But, according to the dream model, these L-shaped structures on the ends of the photon and on the ends of the color charges are monocharges. So it does make sense to think of these ends as being related to charge. And we know that for the quarks, or for the fermions, the ends have to be related to charge because the structures are otherwise identical. So I was kind of stuck there for a while with these ungainly things. You could try using a closed loop string, but the problem with that is it's not a bispinner. You start here, it takes 360 degrees, you're back to where you started. So yeah, you can stick that over the end of the particle, but it doesn't work. But if you take this and you fold it into a figure 8 and then fold top onto bottom, you get this structure. And I initially had said, I can't use that. It won't go over the ends. But then one day I finally said, can it fit inside? And that's when I had my big aha moment. And that's where things really took off. Because yes, you can fit the spinner inside one of these structures. In fact, the fit is extremely good. You can work out based on how these things assemble that this across one of these squares is 1/6 of a string length. And you could also, because you started with a closed loop string and you fold it in 2, you can work out the diameter of this. And this actually occupies almost 96% of the space. There's a little bit of space at the top and bottom and the sides. They come in very close approach. So that immediately suggested that perhaps there was an electromagnetic connection that's holding this all in place. And we used the spinners last time, saying they have 2 distinct sides called 1 plus, 1 minus, to set up a charge field. And so we've got this thing that makes the charge field, but we've also got this thing that connects to the structures that have charge. That sounds like one of the big mysteries out there in physics. What is alpha? So alpha is the fine structure constant, and it quantifies the strength of the electromagnetic interaction between elementary particles. So here we've got charge field interacting with the elementary particles. Sounds right, sounds like it could be. It also suggests that this is why we live in a 3D universe. If you could not fit this in here, you would have no spin half particles. Also, I believe that monocharge interaction between these plus and minus sides are what are holding the particles to the Higgs field. And so you would also have no mass. So this fit suggested why we're living in a 3D universe. So Wolfgang Pauli had, as his lifelong desire, the story was his first question to God when he'd get to heaven would be, what the hell was the alpha constant, was the fine structure constant all about? Where did it come from? Well, I think we've got it. So now let's look at these sizes. The square length and the diameter, the difference between them, which would be, so if we take this side and we take this diameter, okay, the space that's remaining at these two sites is almost exactly alpha, the fine structure constant. The fine structure constant has no units. It's one of these fundamental constants to the universe. Well, alpha is 0.00729, and our space is just a little bit bigger than that. So we're off by 0.00022 for the extra distance. A very, very tight fit for these. And so if you think that there's a magnetic moment around the square, and there's a magnetic moment traveling around the spinner, they come in very close proximity, and we're going to deal with halves, right? We've got that going on here, and we've got that going on here. So let's just pick the top. We've got a gap here that is very small between the two magnetic moments. If we allow the magnetic moments to equal up to alpha, then the gap is 0.0001 string length. Very close on the spacing. So Leonardo da Vinci almost had it right. He's got the square, he's got the circle, but he didn't get the circle completely in the square. So for this next part, though, and this would probably be a good time to take our coffee break, is, you know, we're doing this without magic. So I can't walk on water for you, but I sort of know where we want to get to make all of this work, to get the numbers we need to get. And to get there, I'm going to have to take some leaps that hopefully I can connect enough that you'll accept them. And hopefully they're marching off in the right direction. And with that, let's take our coffee break, and then I'll pick up with showing you how we get that spinner to work with the particle structures of the fermions. Okay. So when we're talking about spin of an electron or a spin of any fermion, any of these particles that are in this diagram you have, we're going to involve the spinner. But if you ask physicists what spin is, you get these very blank, hand-waving descriptions. So Ohanian, who has written one of the main physics texts used to train physicists, had summarized the common perceptions among physicists. According to the prevailing belief, the spin of the electron or some other particle is a mysterious internal angular momentum for which no concrete physical picture is available, and for which there is no classical analog. So it's spinning, but it's not. It's not physically spinning. And then he goes on to talk about, and the reason people said this, Lorentz had pointed, a famous physicist had pointed out when people first started talking about spin of an electron physically spinning, he pointed out that the charge radius of the electron would have to be moving at 137 times the speed of light. Nothing's allowed to go faster than the speed of light. So everyone said, yeah, okay, so there isn't a physical spin. Ohanian then goes on to talk about physicist Belafonte, who had established a spin could be due to a circulating flow of energy or momentum density in a direct field. So not a physical structure turning, but actually a current out in a field. And that could explain spin. So from that, Ohanian maintains that while spin is intrinsic, it's not internal to the particle structure. In contrast, the dream model that I came up with finds that intrinsic spin is due to the magnetic moment on an intercalated spinner. What's that mean? Intercalated is, when we put the spinner inside the square. So don't panic. This is the Dirac equation, and I'm only showing it to you to point out a couple things. And that's that this is the Dirac spinner. It's a bispinner. It's got 4 values to the spinner. And it is related to the electromagnetic field and to the electromagnetic vector potential. So the Dirac bispinner interacts electromagnetically. That's the message I want you to get from that. And also, this wave function is describing the spin states. So spin up or spin down, like we talked about last session. And then the other was that it's tied to the existence and behavior of antimatter. Why do we say that? These are imaginary numbers here. And actually, Dirac, when he derived this equation, had those values, and instead of just dismissing them as being unreal, actually predicted the existence of antimatter. And then it was later found. Okay, so could the Dirac bispinner be a twister? Roger Penrose, who we talked a little bit about last week, has this definition. So he put 2 spinners together to make a bispinner and to make a structure called a twister. But a bispinner is 2 spinners put together. And so the question is, are they one and the same? According to Penrose, the representation of a pair of 2 component spinners gives the simplest type of twister with 4 complex components. That sounds like what we're dealing with. We've got left helicity, up and down spin, and right helicity, up and down spin. We've got the chiralities, left and right chiralities. So what do these things kind of look like? Well, this would be, if you separated charges, you get an electric dipole moment. If you run a current, moving charge gets you a magnetic field, and that gets you a magnetic dipole moment. For spin, we're talking about something a little bit different. So we've got current going around this way, and we're producing spin vectors that are tangential. So spin would be in these directions, going parallel and tangential to the spinner itself. Here's our bispinner. And what I'm going to try and convince you of is that for matter, we're going clockwise around this bispinner. And for antimatter, we're going counterclockwise around the bispinner. So here is the twister that Penrose came up with. And so my supposition is that actually what's going on with this bispinner? We've got these interacting magnetic fields, one going around the square, one going around the spinner, and we're producing this spin toroidal dipole moment right here. So this we need to spend time on carefully, because you can take all those properties in those 4 columns that I had shown you, and you can put them on a structure. So here we have left helicity for matter and right helicity for antimatter. And then we've got left chiral and right chiral and left chiral. And we've got these values that change going from left to right. So for example, the weak isospin goes from -0.5 to 0. And this value, because it's mathematically related, also changes. So how can we explain all these different things? Helicity, chirality, spin, isospin. How do we get them all in one place? Here is our bispinner laid out. And instead of a half twist, we're actually putting in a full twist between these 2 parts. And that's to make the helicity work out. But what's happening is if you start here, let's say matter, the red triangle, we come around this way, we're going clockwise, come down here, go around here, we're still going clockwise, and then back up here. So if we have a traveling magnetic moment moving along the spinner. For antimatter, we're going the other way. We're going counterclockwise here, come down around here, we're still going counterclockwise. That is our difference between matter and antimatter, is your direction around the spinner. So we've got 2 faces here. If you fold this backwards, what you'll find out is that you have your spin changing direction. So up here, you're going clockwise with your spin, and down here, you'll be going counterclockwise with your spin once this is folded into a structure. So we've got our up and down spins from this. And then for the isospin, it really is a reflection of which side of this bispinner you're on. One side is 0 isospin, the other side is -1/2 isospin. And my way of thinking about it is actually we're oscillating the structure on one side of the bispinner is being connected to the Higgs field, and the other side being connected to the particle structure. And that's our bridge between mass and charge. Now note that both the helicity and the weak isospin are going to flip as you go from matter to antimatter. So here the helicity is left for matter, right for antimatter. The isospin is -1/2 for an electron for matter. For a positron, it's +1/2. And again, it's just a matter of which way you're going around this is affecting that. Now, as you're on one of these faces, the value is constant. And so it really transitions as soon as you cross to the other spinner. And I believe that's why these values are quantized. You don't have a continuum between 0 isospin and -1/2 isospin. It is one or the other. And that's because you're on one face or the other face of this. And then as far as chirality goes, so if put your thumb down in the direction this particle is moving, if it's spinning this way, you've got a right chiral particle. If it's spinning the other way, you've got a left chiral particle. And what's happening as you go from side to side is you're flipping the spin, but you're also flipping the chirality because you're changing the direction of the spin relative to the direction of motion. So those 2 are connected. And so you're just constantly oscillating. The particles going left chiral, then right chiral, then left chiral, then right chiral, spin up and spin down, or states that can exist on either of those chiralities. All right, so in that Dirac equation, there was this thing that got ignored. Dirac ignored it because he didn't know what to do with it. It was a term for an electric field, and he didn't see how there was an electric field. And other people approached the subject matter from a different angle, and it just doesn't show up when you do that. But there is an article out there by Engel Rosa, which maintains that that component is actually real, that there's an electric dipole moment, which is analogous to a vibration of an object. So he sees that there is both a spin, so this is an electron, and this is to do with Heisenberg uncertainty principle, which allows the electron to behave like a point-like structure. And there's a rotational spin, but there's also a vibration that occurs along here. That's the anomalous electric dipole moment. I can give you kind of an analogy. If we take hematite spheres, okay, you can rotate one of these spheres, right? But there's also a vibrational energy between them, which you can hear. And that's basically what he's saying, is there's a vibration between these two, energy transferring between these two positions. So if we try to incorporate that with what we've done with our intercalated spinner, what it looks like is that spin, which is angular magnetic dipole moment, is this spin, this coming around the spinner, but that the electric dipole moment is a vibration, which corresponds to going from one face of the spinner to the other. And again, the question is that connected to the twister that Penrose came up with? And the electric isospin vector would then be collinear with a spin toroidal dipole moment. Okay. But our spinner needs to travel in a direction, one given direction. It can't go back and forth between matter and antimatter. Can't keep reversing direction. So the magnetic field will follow a moving charge, and so the spinner will go around, but we need it to go around in only one direction. One way of thinking about all of this is that we get this electric moment by interaction of an electromagnetic field, and our particles would be dipole antennae. And so you have here, they're showing an electric wave going back and forth across it that induces a current flow, and the current flow going through a string would produce a magnetic field because it's moving. But the electromagnetic field oscillates, and so that means we'd be going back and forth on this, and we can't have that. In electronic circuits, there's a way of dealing with that, and that's called a diode. It's a one-way valve. It allows a current to flow in only one direction. We need a diode. And so diode is charges separated in a manner in which when you add current, it can only go in one direction. It can't flow back the other way. Okay, sounds like a tall order, but we do have on our bispinner two distinct sides, which we're calling plus and minus, and that's the basis of our charge field. So now we need a way to get across in only one direction. Well, there is actually a device that is based on quantum mechanics called a Zener diode. And what happens with a Zener diode is that you get quantum tunneling from one side to the other. And so maybe, and again, these are these big steps across those stepping stones, but maybe this spinner in here is functioning as a diode to control the flow of the magnetic moment. So here we've got our electromagnetic wave coming across our dipole antenna. We could look at these structures like that. And so here you would have the field moving in this direction, and over here you would have field moving in the other direction. you can set up a circulation around this structure and come up with a spin. But the question, it doesn't work so well, because when we get down to the electron neutrino, you've got more than one path through there that could make this go this way or this way. Maybe a better way of doing it is to look at this square and have the electromagnetic field, have the magnetic field hit this square. It will induce a current that flows around the square. And all of these structures have the square. So that seems like a nice way to go. And now we're going to add the diode into that circuit. So here's our bispinner. And when we have it functioning as a diode, we get current going around this way. The diode allows that current to pass, and we've got a magnetic moment moving in just one direction around the bispinner. When the electromagnetic field reverses, the current reverses, but the diode will not let that pass. And so the bispinner does not have charge flowing across it at that point. So let's look at the difference between matter and antimatter. In the dream model, matter and antimatter result from different directions around this bispinner. And if the spinner is a diode, then the polarity of the spinner is flipped for matter and antimatter. So that gate has to go in the other direction. Problem with that is that most of these particles I've showed you are symmetric. So it doesn't work that way. And what that suggests instead is that since the particles are symmetric, that what is changing is the orientation of the particle to the electric field. So when you make a magnet, you've got electrons spinning in all sorts of directions. It balances out to zero initially when it's warm. If you've got a ferromagnetic material, and as it cools, those electrons start to align with each other. Now they could have picked going this way, or they could have picked going that way, but whatever they pick, that's a symmetry breaking event. Everything's going to line up along with it. And I believe that's what happened with the universe too, is that. So I had told you last time that I would talk to you about dark matter. And this, when I came up with working with this bispinner, that was the magic moment. It took me in all these different directions to explore. Well, I've got these set structures, and there are properties associated with those structures. And so we can see if any of them meet the definition of dark matter. So dark matter does not interact with the strong force, the weak force, or the electromagnetic force, but it does have mass. Well, the spinner does not have parallel half bonds or an L-shaped piece. And those are what are involved in the strong force. The strong force is when we take a pair of parallel bonds and stick them together as a physical bond. That's the strong force. And it does not have this L-shaped piece, which is the monocharge attraction. So the spinner isn't going to interact with the strong force or the residual strong nuclear force. Spinner does not have any bonds that can be acted on by the weak nuclear force. And I'll talk to you when we get to a third talk about how I think the weak force is working. And it really comes down to what looks like bond rearrangements. The spinner does not have any free half bonds. Those are what are providing charge. So it's not going to be charged. And that means it's not going to feel the electromagnetic force. Now you might say, wait, you just put plus and minus charges on this thing. But it is analogous to the way a photon is. So a photon is an electromagnetic wave, but it does not get influenced by an electric field. If you run an electric current through a wire, okay, or if you have plus and minus charges separated, you can't make that light beam move. You can't get a magnet and pull light to you, okay? Even though it is the electromagnetic force carrier, it does not have an electric charge associated with it. Same here. It does have mass. Why? Because I think that the bispinner, the faces on that, are actually interacting with the same thing on the Higgs field. So you can envision the Higgs field as being a superposition of these. Because they are integer spin 1 particles, well, this would be spin 0 particle, you can stack them on top of one another. And so you could think of the Higgs field as a bunch of these, each face having a spinner in it. That's what is plus to minus charge attraction, monocharge attraction, I think is the basis of mass. So they would have mass based on that. Okay, so dark matter does not interact with strong, weak, or electromagnetic force, but it does have mass. Only closed loop structures are immune to the electromagnetic force, strong force, and weak forces. The spinner is a simple closed loop structure that would have formed readily and abundantly during the Big Bang. Spinners should be relatively stable structure. We've got a closed loop string that's just folded. This is consistent with there being a stable ratio of regular matter, baryonic matter is called regular matter, and the primordial and the ratio that was present in the primordial universe. So that ratio has been constant throughout the entire history of the universe. Stable structure would meet that. And then last time I talked about this fuzzball notion of black holes, where you avoid the singularity and you avoid the information paradox for black holes by actually breaking matter down into strings as it enters the black hole. And so they're fuzzballs. There's these big balls of string that sit just below the event horizon. Well, that model equates a string with dark matter. A black hole, when you think about it, doesn't interact with anything. It has just momentum and mass. So the intercalation of the spinner into each of these particles would provide mass to the standard model particles. If we just had empty particles like this, structures like this, they would be massless. It's because they have the spinner inside the square that they have mass. And that's going to allow us to do a calculation. So this precisely predicts the abundance of matter relative to regular matter relative to dark matter. That ratio is 1/6, and there are multiple lines of evidence for that. So the size and angular momentum of galaxies, this is how they first noted there was dark matter. And that provides a ratio that comes out to 1/6. The primordial ratio of deuterium to hydrogen, so when the universe is first born, also results in a ratio of 1/6. And fast burst radio measurements also produce estimates that come out to 1 part of regular matter to 5 parts of dark matter. So when you look at the total proportion of regular matter, it's 1/1 + 5, so 1/6. How's that work? Well, our universe is made out of G1 fermions. That's essentially all there is in terms of the matter. Well, a G1 fermion is what you get when you put 4 strings together. And then the spinner in the center makes a 5th string. So to make an up quark or a down quark takes 5 strings. You could take those 5 strings and produce 5 bispinners with them. So for every particle of regular matter, you could make 5 particles of dark matter. That's our ratio. You get 1 baryon, and then for total matter, you get the baryon plus you get the 5 dark matter strings that you can build. That's a 1-to-6 ratio. It's exactly what you would expect it to be. Also, the spinner would account for the distribution of matter and dark matter. If you didn't have loss of momentum, things would just orbit infinitely. They would never come together. And there's this model proposed by Larson and Broom for why the universe looks the way it does. When you look at a galaxy, the matter's in the center and the dark matter forms a halo around it. How did we get there? Well, they say that the fundamental particles of matter are formed from protons and neutrons and atoms. The formation of molecular hydrogen allowed energy loss through radiation. So now you can lose momentum through radiating out energy. So that energy loss allows matter to aggregate. Dark matter cannot radiate. So therefore, it's going to remain at maximal entropy. Dark matter is going to remain dispersed. The aggregated matter is going to fall to the center. It's going to collect in the center. And that's going to result in a halo of dark matter that's gravitationally locked to a central region that's enriched for regular matter. And as an isolated closed loop quantum string with half spin, a spinner cannot radiate or aggregate. This matches the behavior of dark matter. Well, what about other sources of mass? I had told you in the first talk, the estimates of how much regular matter are out there are based on astronomical observations, and they're mostly looking at hydrogen, which is made up of up quarks and down quarks and massless gluons. But last week, I showed you that only about 1% of the mass of a proton or a neutron comes from its quarks. The rest comes from the kinetic energy of the gluons, gluon binding energy, and some quantum effects. All right, so how's that going to work then? Well, in order for the string ratios to account for the mass ratios that we see, then the gluon kinetic energy, the gluon binding energy, and all the other bits that add up to this 99% must be derived from the energy carried by the constituent strings. Okay. And then quickly, these are pions in the standard model. They are what allows one proton to connect to another proton, which keeps them from flying apart because they both got positive charges. And you can build them out of, here's up and an anti-up quark put together, and then you've got colored charges on the ends. Over here, we've got down and anti-down, and here we've got either an up anti-down or a down anti-up. And so we have charges, when you work that out, of 0, or here +1 or -1. And the masses are, and I want you to remember this number, 135 approximately mega electron volts per speed of light squared. So this, sorry to jump. These, instead of being the pions, are the rho mesons. They're exactly the same structures. They have exactly the same constituents, yet they have dramatically different masses. So how can the same structures, and they differ in their spin states? So the pions are spin 0, and the rhos are spin 1. How can they differ in spin number? Well, you could arrange spin like this so that they cancel each other out to give you spin 0, or you can arrange them like this so that they reinforce. So you can have both of them pointing down or both of them pointing up. That gives you spin 1. How's that produce different masses? Well, Sakharov, the famous Russian physicist, solved that a long time ago. He wrote an equation that actually allows you to calculate the masses of these particles based on their spin states. So when the spin coupling is spin 1, you get a multiplication of a quarter. When it's spin 0, you get a multiplication factor of -3/4. So it falls out of the math. It actually gives you the right answers. All right, so I'm out of time. And so we will pause it there, although we nearly got to the end of it. And we'll pick up the next piece whenever we get a third session. Thank you.
Wow, I can't thank you enough, Eric, for giving us something to think about and having the energy and creativity to come up with that model. Thank you so, so much. Okay, before we go with the talk, I just have a few little announcements to make. One, before I forget, is we'll have lunch afterwards for those who are interested at the Hibachi Grill and Buffet at 12183 Katy Freeway. That's a first for us. We've never been there before. And on Wednesday, we have the Houston Oasis Cards Group. That's a weekly event. And if you're interested, Rich or Jennifer in the back can help you with that. On Saturday, we have the Houston Oasis Bike Club outing. That's a weekly event, weather permitting. And if you're interested, get with me after and I'll put you on the email list. And on February 1st, we have the next book club meeting. And this would be a good one. If you considered being in the book club, it's a pretty easy book to read. It's an interesting one. The hardest thing about leaving, and to be honest with you, you can come to the meeting even if you haven't read the book, but that's just an inside tip there. The conversations are always interesting. And so I guess that's about it. Oh yeah, and we have the welcome table in the back. If you need a name tag, or if this is your first time at Houston Oasis, please go back and see Jennifer and Paige back at the welcome table. And if you need the standard model of the particle physics, elementary particles, Richard has copies in the back there, some hard copies. And if you'd prefer having the electronic version, he can also email that to you so you can have it on your smartphone. And now we're going to have a quick announcement from Terry and then a last song from Ryan.
Hello, everybody. Many of you have heard that the Winter Street Studios, there was an unfortunate fire explosion at Winter Street Studios. And one of the people that has come and spoken to us many times and who has been a member of this community is Laura Spector. Her studio was affected by it. And she's had the people come out and do the fixing of the paintings and things like that. But she does need some help. And so we thought we would do an Oasis help at the Winter Street Studios next Sunday at 2. It's not a lot of work. Mostly she wants her easels cleaned and maybe if anybody knows how to stain and refinish things. But I thought that it would be a really wonderful thing. Since she was here recently, she did the story about the whole show that was at the Jung Center. I don't know if y'all remember and Shed the Paints, that's her. All those pieces were safe. But anyway, next, Alexis is going to put it online, but next weekend, Sunday, at 2, and we'll meet at Winter Street. Anybody that wants to come. All right. Thank you.
I can see clearly now the rain is gone. I can see all obstacles in my way. Gone are the dark clouds that made me blind. It's gonna be a bright, bright, sunshiny day. It's gonna be a bright, bright, sunshiny day. I don't know if we have a culture in here of singing along, but you're welcome to if you want. And I can see clearly now the pain is gone. All of the dark clouds that led me astray. I think I can see the rainbow I've been hoping for. It's gonna be a bright, bright, sunshiny day. It's gonna be a bright, bright, sunshiny day. Look all around, there's nothing but blue skies. Look all around, there's nothing but blue skies. I can see clearly now the rain is gone. I can see all obstacles in my way. Gone are the dark clouds that made me blind. It's gonna be a bright, bright, sunshiny day. It's gonna be a bright, bright, sunshiny day. It's gonna be a bright, bright, sunshiny day.